Morning to all. Myself, Dr. J.J.Jayapal, Assistant Professor, PG and Research Department of Computer Science, St.Joseph College of Arts and Science, Autonomous Cuddalore. Today, we are going to see the computer architecture. The subtopic is RASC pipeline. Basically, we have the three pipeline conflicts. The pipeline conflicts are difficulties in instruction pipeline. Difficulties cause the instruction pipeline deviate from its normal operation. They are the three conflicts. The one is resource conflict, second data dependency, third branch difficulties. First one, resource conflict. It causes by access memory by two segments at the same time. Most of these conflicts can be solved using separate instruction and data memories. The second one, data dependency. When an instruction depends on the result of a previous instruction. Third one is branch difficulties. It arrives from branch and other instruction that change the value of PC. Delayed load. It performed by the computer with inserts no operation NOP instruction to ensure that the data dependency is satisfied without the need for additional hardware. Handling of branch instruction or solution to branch difficulty. Prefetched target instruction. The prefetch both possible instructions in the case a conditional branch. Branch target buffer. Each entry in BTP branch target buffer consists of address of previously executed branch, instruction, target, instruction for that branch, next few instruction after the branch target instruction. Loop buffer. When the program is reduced in the name program, it is stored in the log buffer including all branches. This program loop can be executed directly without memory access until the loop mode is removed by the branch instruction. Branch prediction. It uses some additional logic to get the outcome of your conditional branch instruction before it is executed. Delayed branch. In this procedure, computer rearranges instruction in order to keep the pipeline full. It inserts no operation or some other useful instruction after each branch. RAC pipeline, reduced instruction set computer characteristics. The RASC to reduce execution time by simplifying the instruction set of computer. Relatively few instruction addressing modes, memory access limited to load and store. Fourth one is all operations done within the registration of a CPU. The fifth one is fixed length, easily decoded instruction format. Sixth one, single cycle instruction execution. The last one, hardware rather than microprogrammed control. Generally, pipelining using a small number of sub-operation executed in one clock cycle called single cycle instruction pipeline. The RAC pipeline can be implemented in three segments. The one is instruction fetch. We simply indicated ALU operation. That is A, execute the instruction E. The IAE, I instruction fetch, it fetches an instruction from memory. ALU operation, execute the instruction in ALU. E. Execute the instruction. Store the result of the ALU operation in the destination register. The RISC machine uses two separate buses with two memory. Once for storing the instruction, two other for storing data. RAC architecture translate high-level language program into machine-level language programs. So they are two loaded. The one is a delayed load, another one is a delayed branch. It is used to solve the data conflicts in instruction pipeline. The first one is a delayed load. I take the one example, the following instructions. Load R1 is equal to memory address of 1, load R2 memory address of 2, add is addition R3, R1 plus R2, and then finally store the data's memory address of 3. The pipeline timing with the data conflict, the one timing diagram, it's created with the conflict of data. So clock cycles, that is the top row 1, 2, 3, 4, 5, 6, and then the load one, that is operations load 1 R1, load R2, add R1, R2, store R3. Here, the first clock take the load the R1. I means and the I is it is fetching the instruction. A means the ALU operation. The E means that is execute the instruction. So pipelining means we have to do the parallel operation. That is a sequence of operations. Likewise, load R2, that is a IAE, fetch the instruction, ALU operation and execute the instruction. The third one is add the R1 plus R2. What will happen here? The adding the R1 plus R2 means we are before the load R2, we have to add the R1 plus R2 means it will creating the data conflict. So data, it's creating the data conflict means we can't do the operations and store the instructions. So here we are adding the one no that is a NOP operation after the load R2. Okay, you see the timing diagram, the clock cycle likewise 1, 2, 3, 4, 5, 6, 7. At load R1, it is I is the fetch the instruction, A is the ALU operation, E is the execute the instruction. Load R2 the same. Here that is a, we are inserting on no operation means it will be take the one more empty clock cycle for loading the R2. After that, the add R1 plus R2 means the data is available and we can easily fetch the data and add the two values R1 plus R2 and then finally stored into the R3. So that diagram, that timing diagram, it is representing with inserting the NOP, that is no operations. Okay, if the three segment pipeline without interruption, there will be a data conflict in instruction 3 because the operand in R2 is not yet available in the A segment. The no operation instruction inserted after the lower to instruction. The no operation instruction used to advance one clock cycle data conflicts in the pipeline. So the second one is a delayed branch. A branch instruction delays the pipeline operation until the instruction at the branch addresses is fetched. The RISC processor is to delay on the compiler to redefine the branches to that they take effect at the proper time in pipeline. This method is referred as a delayed branch. So that is a zero diagram for the delayed branch timing diagram. Using no operation instruction, the clock cycle likewise 1, 2, 3, 4 up to 10. We are doing the some more instruction. We are using the some more instruction example. Load from memory to R1, increment R2, add R3 to R4, subtract R from R5 from R6, branch to address X. So here we are implementing in the timing pipelining, timing diagram, a load IAE and then second instruction is the increment. Here the it is not a depending it is not depending the previous instruction. The each instruction is independent, means we can easily to rearrange the instruction. So load, first one is a load, that is R1, and then increment R2, and then add, and then subtract, and then we are finding the branch to X. When you are finding the branch to X means we need the two no operations. So that is, it is update the update, it is update, update the pipeline, and again another one is empty the pipeline, again fetch the new instructions. So we need the inserting the no NOP operations. The sixth one is the NOP, and then seventh one is the NOP, and then finally last, that is the instruction in X. Here, that is, we are using the clock cycles, 10 clock cycles, but 8 instructions. But here, we are rearranging the instruction. How we are rearranging the instruction means it's not, it is not a depending the instruction to the previous one. Each instruction is independent. It is not dependent to any other instructions. Now here we are rearranging the instruction, the clock cycle 1, 2, 3, 8, and then load IAE, increment IAE. Now we are branch to X. The branch to X means that is the IAE, and then add IAE, subtract IAE, and then insert in X, instruction in X. IAE. So that means after branch we need the two empty cycle. Here we are removing the NOP operation, the no, two empty cycles we are removed from the clock cycle. We have to do the some other operations. It's like that addition and the subtraction. Now we are reducing the clock cycle and reducing the operation mean operations. Okay, thank you.